Welcome everybody to the High Energy Density Science Center Seminar Series. It's good to have with us Dr. Simon Blouin, who is Director Stock Fellow and Los Alamos National Laboratory's ex-computational physics division. He obtained his PhD from the Université de Montréal in 2019. His thesis focused on the modeling of the atmospheres of white dwarf stars. For this work, he was awarded the 20 Bosquet Medal for the most outstanding thesis in astrophysics in Canada, as well as the PhD prize of the International Astronomical Union for the best thesis in the Stars and Stellar Physics Division. His writing at Los Alamos research is centered on the interiors of white dwarf stars. And very much looking forward to his interesting talk on white dwarfs. And a quick announcement: we are going. This talk will be recorded, so anything you say or do will be for the record. If you have any questions, please type it into the chat field, and I will read them at the end. And also, we will not have a talk next week because of APS-DPP, and I hope many of you who are attending have a good time. And otherwise, please take it away, Simon.
Okay, well. Thank you for this introduction. So this talk is about white dwarf stars, and more specifically about a new simulation capability that we've developed to model phase transitions in dense plasmas and how this is relevant to white dwarfs. So this talk should be very accessible to anyone, even if you don't know anything about white dwarfs yet. So in the first section of my talk, I will take time to explain what a white dwarf is, why they are interesting objects, and what we can learn from those objects. Then I will move to really explaining the phenomenon that's of interest here, which is the core crystallization of white dwarfs, where the carbon-oxygen plasma that makes up the interior of those stars undergoes a liquid to solid phase transition. This will then motivate the work that we've been doing on computing phase diagrams for such dense plasmas. And finally, I will conclude by comparing the predictions of our calculations to actual astronomical observations. So what is a white dwarf? So the vast majority of stars in our galaxy will end their lives as white dwarf. So it's the stage that is reached once the star has exhausted all its fuel during the main sequence and giant phase. So it's just this little tiny core that is left behind after the planetary nebula phase. So for the 3% or so of stars that don't become white dwarfs, that's just because they're too massive, so they collapse into either neutron stars or black holes. Most of the mass of a white dwarf is contained within its core, which is usually made of carbon and oxygen. And this is surrounded by a helium envelope, making up about 1% of the white dwarf's mass. And then there's also a thin layer of residual hydrogen, so hydrogen that was not burned up during previous phases. So the conditions that we find in white dwarfs can be quite extreme. So at the center, we're talking typically about densities of 10 to the 6 gram per cubic centimeters and temperatures of the order of 10 to the 6 Kelvin. So because white dwarfs are so dense, they are of course very compact objects. So typically we're talking about 0.6 solar mass compressed into a volume comparable to that of the Earth. At the other extreme of the density temperature spectrum, we have the atmosphere of the white dwarf, which is the only region that we can directly see. So it's very important for this reason. But this region is, the conditions are much less extreme. So typically it's gas-like densities and temperatures between 3000 and 10 to the 5 Kelvin. So probably the most important property of white dwarf is that because those are objects that have already exhausted all their nuclear fuel, the only thing that they can do for the rest of their existence is to simply cool down in a monotonic fashion. So here I'm showing the surface temperature of a white dwarf as a function of its age. So this may look like a quite boring evolution for a star, But this borrowing evolution actually has many advantages. The main one being that it enables astronomers to measure the ages of white dwarfs quite easily. So the idea is that we can determine the surface temperature of a white dwarf from spectroscopic observations, and then using cooling models of white dwarfs, we can translate this temperature into an age. If we go into the details, we also need to care about the white dwarf's mass and about its composition, because those are two parameters that will affect the rate at which the white dwarf can cool down. But the important point here is that those three parameters can be obtained quite easily by comparing spectrometric observations to model atmospheres of white dwarfs. So this is something that can be done very accurately. And then you only have to take your cooling models, and from that you extract the age of the white dwarf. So this is a technique that has been used now for about 35 years. It's still being refined because there are many uncertainties involved in this approach. But throughout the years, it has been used to measure the ages of different stellar populations in our galaxy with much more accurately in general than what can be done with other methods. So what happens is that in general, stars have observable properties that change very little over time. So you end up with large uncertainties if you try to measure their ages. But with white dwarfs, because we have this continuous cooling, it's much easier to discriminate between different ages. So that's really what makes white dwarfs so useful to astronomers. More recently, as we are getting more and more observational data and better statistics, people are starting to not just look at the total age of a stellar population, but instead look at its formation history. So here, for instance, I'm showing recent results of the stellar formation rate in different components of our Milky Way. And we now have good enough statistics to resolve interesting features in there. So this peak, for instance, has been linked to the merger of our galaxy with a nearby satellite galaxy. So those kinds of events are known to trigger a burst in stellar formation. So we're now able to resolve this kind of thing just by looking at the ages of white dwarf and reconstructing the history of the stellar population. So this is obviously very interesting to astronomers because it allows us to better understand how our galaxy was formed and has evolved, and ultimately how we got here. But all those applications, ultimately, they depend on the accuracy of the white dwarf cooling models that we use to translate the surface temperature of the white dwarf into an age, which is really the quantity that's the most interesting here. So those white dwarf cooling models, they depend on a lot of physics. And the physics is actually not always well constrained because we are in regimes that are quite exotic. And one phenomenon in particular that is still, that we know that we still don't model exactly right is the core crystallization of white dwarf. So as I said earlier, the density in the center of white dwarfs is very high. And this means that the carbon-oxygen plasma is completely ionized, and the electrons are completely degenerate. So if you look at the interior of a quite relatively hot and young white dwarf, you would see that the carbon and oxygen ions can move around pretty much as they wish. But as the white dwarf cools down, the ions become increasingly correlated together, and at some point they are so correlated that they freeze into a lattice structure. And this is what we call the core crystallization of white dwarf. So it's a first-order phase transition from liquid to solid, meaning that there is a release of latent heat during this phase transition. So this release of latent heat is very consequential for the white dwarf evolution because it's a new source of energy for the white dwarf, which means that it will slow down its cooling process. And actually, models show that it slows down the cooling of white dwarf by about 1 billion year. So obviously, it's something very important to include in white dwarf cooling models. So this core crystallization phenomenon was predicted to occur back in the 60s, but it's only 2 years ago that we got the definitive observational proof that this really does happen. So here I'm showing a scatter plot of the mass and temperatures of white dwarfs in our solar neighborhood. So every circle is one white dwarf. So the first thing to notice is that most white dwarfs are clustered around 0.6 solar mass, because that's just the most frequent mass for white dwarfs. And of course, on a plot like this, the white dwarfs, they evolve along horizontal lines, so at constant mass, but decreasing temperature. So the interesting feature here is this kind of diagonal sequence that we can see. And this turns out to be the signature of core crystallization. So what happens is that when white dwarfs are within this blue region, they are in the process of releasing this latent heat, which means that they are cooling down more slowly. So that's why we see a kind of a pileup of objects in this region. So it's basically just a traffic jam of white dwarfs that are evolving more slowly. But to complicate the matters a little, crystallization occurs at the same time as another important phenomenon for white dwarf evolution, which is known as convective coupling. So for the bulk of white dwarfs, so for 0.6 solar mass white dwarfs, both of those things happen at the same time. And convective coupling also imposes a cooling delay to the white dwarfs. So it's not obvious at all how we can really distinguish between the effect of crystallization and convective coupling. So the key to be able to detect the signature of crystallization is to look at massive white dwarfs, for which crystallization occurs well before convective coupling. But to do that, we needed to know the masses of a large sample of white dwarfs, and that's something that we were able to do only very recently. So very rapidly, what convective coupling is, so when the white dwarf is still quite hot and young, you can basically divide its structure into 3 different zones. So you have the interior, which contains degenerate electrons, so it's very efficient at conducting heat. So this is highly conductive. The uppermost layer is the convection zone, which is also very efficient at transporting heat. But in between those 2 zones, there is a region that is neither convective nor very conductive, which means that it's less efficient at transporting energy. So it acts like a buffer for the white dwarf cooling, and it stops the white dwarf from cooling down too fast. But when convective coupling is reached, the convection zone reaches into the degenerate interior. So at this point, the whole white dwarf structure is very efficient at transporting energy. So when this happens, you suddenly have a lot of excess heat to get rid of. So the surface temperature will cool down more slowly for some time while you're getting this excess energy out of the star. So since we don't want to bother with convective coupling and really be able to study crystallization in isolation, we had to look at massive white dwarfs. So the reason why it's only 2 years ago that we were able to detect this sequence is thanks to the first major data release from the Gaia satellite from the European Space Agency. So what this satellite does is simply measuring the 3D positions of billions of stars in our Milky Way. And here, the third dimension, so the distance of stars to us, is really what matters for our problem here. Using stellar parallaxes, Gaia was able to measure the distances of 250,000 white dwarfs, and this is what allowed us to measure their masses. So before Gaia, doing those parallax measurements from the Earth is very time-consuming and not that accurate, but Gaia was really is really specialized in getting those measurements very precisely. Now, what's the relation between getting distances of stars and getting their mass? Well, it all comes down to this simple geometric relation. So on one hand, we know the observed flux of a given white dwarf from the Earth, and we also know its distance thanks to Gaia. And on the other end, we also know the intrinsic or surface flux of the white dwarf because we have accurate model atmospheres for those stars. So from this relation, so I mean, the only thing that's between the observed and surface flux is simply the solid angle of the white dwarf. So from that, we can get the radius of the white dwarf, and then white dwarfs obey a very well-determined mass-radius relationship. So from this radius, we can extract the mass of the white dwarf. So that's how Gaia really changed the face of the white dwarf field by providing all those masses. So in the pre-Gaia era, the problem was that we nearly always had a degeneracy between the radius and the distance of white dwarfs, which is why we were not able to detect this crystallization sequence. So now we will concentrate on white dwarfs that have masses between 0.9 and 1.1 solar mass. And the reason for this is that we want to take only stars that crystallize well before convective coupling, and also that we don't want to take too massive stars because very massive stars have different core compositions. So oxygen neon, for instance, instead of carbon oxygen, but we want to concentrate on carbon oxygen because that's the core composition of the vast majority of white dwarfs. So the way astronomers like to look at this kind of thing is by plotting a luminosity function, which really should be called a luminosity distribution. So what we're seeing here is simply what is the abundance of white dwarfs for different luminosity bits. So in red, we see the observations from Gaia. So here on the left, we are talking about very hot and luminous white dwarfs. So that would be those stars in the left corner of the mass temperature plot. And at very low luminosities, now we're talking about the very cool one at the right hand of the plot. So the interesting feature is this bump that we see here, and this corresponds to our crystallization sequence. So that's where white dwarfs are in the process of crystallizing, which means that they're evolving more slowly. So that's why we see this overabundance of objects. So this was, this discovery was published in Nature in January 2019. And of course, what people tried to do right away when this was detected is to use the existing evolution models for white dwarfs to try to reproduce this pilot. So here in black, I show three attempts to do so using different implementations of core crystallization. And we can see that, well, in each case, we have the problem that the models predict that crystallization occurs too early compared to the observations. And the other problem, which is probably more important, is that we are underestimating the number of white dwarfs in this crystallization pilot. And here, this is a log scale. So actually, there's a factor of about 2 between the observations and the model predictions. So what this means is that we are underestimating the cooling delay caused by core crystallization, which means that the ages of white dwarfs that have already undergone crystallization have to be revised because we know that we are missing a cooling delay in the white dwarf history, and it turns out to be something of the order of 1 billion years. So obviously, This is very worrying for age dating applications. We like to say that white dwarfs are very precise cosmic clocks, but this kind of results tell us that we need to go back to our models. And until we can resolve this problem, we have to take the age determinations with a grain of salt. So this is what motivated us to start working on the calculation of phase diagrams for dense plasmas, and in particular for applications to white dwarfs. So I've already explained that core crystallization releases latent heat, which is important for the white dwarf cooling. But there's another effect that is actually as important as the release of latent heat, but that is less well constrained than the release of latent heat. And this is the phase separation that the white dwarf, that the plasma undergoes during white dwarf crystallization. So the way this occurs is that at first, the white dwarf starts to crystallize at its very center because that's where the density is at its highest. So that's where you reach the appropriate conditions for solidification first. But as the white dwarf cools down, the crystallization front slowly moves upward. But now the funny thing that happens is that the solid crystals that are formed at each new layer that crystallizes are enriched in oxygen compared to the average oxygen abundance in the liquid mixture. And because of that, as the crystallization front moves upward, you are building a concentration gradient where you have more oxygen near the center of the white dwarf and less oxygen near the outer layers. So by redistributing the oxygen ions like this, you are releasing gravitational energy, and this, current models predict that this imposes a cooling delay of about 1 billion years for the white dwarf cooling. So in total, the core crystallization accounts for a cooling delay of about 2 billion years. So 1 billion years from latent heat release, and 1 billion years from this phase separation process. So to know exactly how much gravitational energy is released by this phenomenon, we need to accurately know the shape of the carbon-oxygen phase diagram. So here, the y-axis is the temperature in unit of the melting temperature of a pure carbon plasma, and the x-axis is the oxygen number fraction in the plasma. So everything that's above this liquidus line is always liquid, and everything that's below this solidus line is always solid. So at first, the white dwarf core has a given oxygen concentration, and it will simply cool down at this constant concentration until it reaches the liquidus. When it reaches this point, it will start to form solid crystals, and those crystals will be enriched in oxygen by an amount that is given by the separation between the liquidus and the solidus. Now, because we have formed some crystals that are enriched in oxygen, it means that in our liquid we have lost a bit of oxygen, so we are moving to the left along the liquidus line. So the liquid is being depleted in oxygen, and this process will continue for many millions of years. So you will deplete the liquid in oxygen and form oxygen-enriched solid. And eventually this stops because we reach a point in the phase diagram where the liquidus and the solidus touch each other. So this is the azeotrope point. So past this point, there is no more phase separation, no more gravitational energy release. So the white dwarf will simply crystallize at a constant concentration. So obviously, it's clear that we need to know the shape of this diagram very accurately for white dwarf models. So first, we need to know exactly the melting temperature. So we need to know where this line lies because it tells us when this process starts. Then we need to know the separation between the liquidus and the solidus because this tells us the magnitude of the oxygen sedimentation process. And finally, we need to know exactly where this azeotrope point is because it tells us when all this stops, so when the gravitational energy release stops. So the importance of this phase diagram has been recognized for many decades. So there have been many attempts to compute this phase diagram as accurately as possible. So we can divide modern attempts to do so in basically two categories. So the first option is to use analytical free energy models. So you build a free energy model for your liquid and a free energy model for your solid. And basically you just look at where they meet each other, and this gives you the melting temperature. So the way this works normally is that people use those kinds of mixing rules where their functions, their free energy functions are fitted to the results of Monte Carlo calculations, typically. But what we know is that, what we see in the literature is that depending on the arbitrary choices that are made for the functional forms of those fits, people can find very different results. So it can be so bad as changing the qualitative shape of the phase diagram. So some will find that there is no azeotrope point, and others will find that there is an azeotrope point. And this kind of discrepancy is even found when people are using the same Monte Carlo calculations to build their fits. So the problem is that the differences in free energy between the liquid and the solid that we are talking about here are very, very small. Even a small error in the fitting of those results can be enough to completely change the results of the calculations. Another more sophisticated approach that has been used is to use two-phase molecular dynamic simulations. So here the idea is that you build a large system where you put in contact a solid carbon-oxygen plasma with a liquid carbon-oxygen plasma. But then you let the ions diffuse from the liquid to the solid and from the solid to the liquid. And at some point, there is an equilibrium that is reached in this diffusion. And this will directly give you 2 points on your phase diagram. So the simulation is performed at a fixed temperature. So for this fixed temperature, you just measure the concentration of oxygen in your solid, and it gives you this point. And you measure the concentration of oxygen in your liquid, and it gives you this other point. The main drawback with this approach is that, well, it's very computationally costly, and to make things worse, it's very sensitive to finite size effects. So because we have a liquid-solid interface here, it kind of breaks the symmetry of the system, so it makes it prone to finite size effects. And what we see in the literature is that those simulations are so costly that people don't seem able to push them to large enough systems to completely get rid of those finite size effects. So with those limitations in mind, we decided to develop a third avenue to compute phase diagrams of dense plasmas. This method is called the Gibbs-Duhem integration technique. But really, it should simply be called the Clapeyron integration technique because it's based on the Clapeyron equation. So it's a technique that has been used in the past for neutral mixtures, but that has never been used up until now for plasmas. So it turned out that there were quite a few complications to adapt this method to charged systems because you have to include the electrons, for example. But this is the idea is the same as with the method that has been applied in the past for neutral mixtures. So the way it works is that you simply start from a point in the phase diagram for which you already know the melting temperature. So an obvious choice here is to simply take the pure carbon plasma for which we already precisely know the melting temperature. And then to map the rest of the phase diagram, what we do is that we integrate the phase diagram directly along the melting curves using this version of the Clapeyron equation. So here we are integrating in the fugacity fraction space. So the fugacity fraction is directly related to the difference in chemical potential between the oxygen and carbon ions. And it's built in such a way that when the fugacity fraction is 0, it means that you have no oxygen in your system. And when the fugacity fraction of oxygen is 1, it means that all the system is made of oxygen ions. So really what we're doing here is that we're integrating this function from 0 to 1 in the fugacity fraction space. So in order to do that, we need to evaluate those terms. So we need to know what is the fraction of oxygen ions in the liquid and solid phases for this given fugacity fraction and this given temperature and for a given pressure, because the whole phase diagram is computed at a fixed pressure. And we also need to know the molar enthalpies of the liquid and solid. So to evaluate those terms, we use Monte Carlo simulations that are performed in a semi-grand canonical ensemble where the pressure is constant, the temperature is constant, the total number of ions is constant, and the fugacity fraction is constant. So I will explain how those works just in the next slide. But now let's assume that those are given quantities. It allows us to compute this derivative and start our integration of the phase diagram. And then we just repeat this process until we have completely mapped the phase diagram. So the steps that we do here can be as small as we want. So this can be as accurate as we wish. So here we did it with 50 points from 0 to 1 in the fugacity fraction space. And well, it gives a smooth enough result for white dwarf applications. So the way our Monte Carlo simulations work is that at each iteration, there are 3 types of moves that you can make. So the first type of move is the same that you would have in your typical NVT Monte Carlo simulations. So you can have an ion displacement. And the probability that this displacement is accepted depends on by how much you are reducing the total energy of the system. When we are simulating the solid phase, it's a bit different because now we don't want our solid to melt. So the ions are trapped around their position on the BCC lattice. Now where things become a bit more different than NVT Monte Carlo calculations is that the volume and the number of ions of each species is not fixed, because those are not fixed quantity in our statistical ensemble, which means that the volume of the simulation box can change, and also any ion at some point can change its identity, so it can go from a carbon ion into an oxygen ion or oxygen to carbon. And those tests are here to ensure that we reach the targeted pressure in our simulation and also the targeted fugacity fractions, because those are the quantities that are fixed in our semi-grand canonical ensemble. In more details, the way it works during the simulation is that at each iteration, it's a random choice whether we're doing a particle displacement, a volume change, or an identity change. And the probability that any of those moves is accepted is given by this function here. So if we do a particle displacement, we only look actually at the energy. We want to minimize the energy. If we do a volume change, then we need to include those other terms to make sure that we reach the targeted pressure. So for a volume change, for instance, if we only look at the energy, the system will always want to expand and expand and expand, because this is what will minimize its energy. But those terms are here to counteract this tendency. And if we do an identity change, then we need to look at the change in energy and also at this other term here. And once again, this term here is here to counteract the tendency that we would have if we only look at the energy. So if we only look at the energy, the algorithm will want to transform all the oxygen ions into carbon ions because they have a weaker Coulomb interaction. So this is here to counteract this tendency and make sure that we reach the right fugacity fraction. Now, in terms of the physics that's included in our simulations, so here I'm showing density, temperature profiles of white dwarfs, and the darker region here is the white dwarf core. So this is really the regime in which we are interested. So the first thing to say is that the plasma is completely ionized in those conditions, which means that we are including an electron helium in our Monte Carlo simulations. And this helium is made of completely degenerate electrons, and they are also partially relativistic under those conditions. The ion-ion interactions are computed through a Yukawa potential, so it's screened by the partially relativistic electrons. And this screening term here, this kappa, is recomputed during the simulation because it depends on the electronic density, which changes here because our simulation box can shrink or expand, and also because of the identity changes of the ions. One thing that we are not including is the quantum behavior of the ions. So we are starting to be in a regime where this could matter. We don't think it's a dominant effect, but it's certainly something that we would like to include in the future. So here in red, I'm showing our final carbon-oxygen phase diagram obtained through this integration technique. And I'm comparing it in blue to results that were obtained using molecular dynamics simulation. And those results were widely considered as the state of the art for white dwarf models. So we can see that our method has the advantage of yielding a much smoother version of the phase diagram. And this is important because we want to know for any concentration what exactly is the separation between our two curves, because this tells us how much there is oxygen sedimentation. And the other thing is that it's much less noisy. So in particular, we have a much better resolution of where the azeotrope point lies. So with the molecular dynamics simulation, it's not that clear. Another thing here is that it took only 5,000 core hours to compute our phase diagram, while it took something of the order of 1 million core hours to obtain the one with the MD approach. And it's actually worse than that because our phase diagrams has a resolution 10 times superior to that of the MD approach. So really, it's many hundreds of times more efficient than this two-phase molecular dynamics approach. Other important advantages include the fact that we are performing all our calculations in the right statistical ensemble, and in particular, everything is done at constant pressure and not at constant volume. So in nature, phase transition do not occur at constant volume. And that's why ice floats on top of water. They occur at constant pressure. So that's something that you don't have with the MD simulation approach. You are forced to do it at constant volume. Another important point is that we have directly access at no additional cost to the thermodynamic properties of the system directly at the phase transition, because we are integrating directly along the melting curves. So things like latent heat are readily accessible. Now, something that we want to do in the near future is to take this new simulation capability and apply it to other non-astrophysical systems, such as alloys. So the idea is that now that we have this working Monte Carlo code and this working Gibbs integrator, we can just replace our pair potential by the pair potential of some atoms that are relevant for an alloy, for example, and we can very efficiently obtain the phase diagram of this alloy. We are also working on developing a version to compute ternary phase diagrams of mixtures or alloys. So this is something that is impracticable with the molecular dynamics approach, because already if it takes you 1 million core hours just with two components, then if you add a third component to your phase diagram, it means much more calculations to do. So it cannot be scaled to ternary mixtures. But our approach, with our approach, we have ample room to scale it with a third dimension in the integration. Okay, so now let's look at what happens when we put our phase diagrams in white dwarf models and how it compares to observations. So I'm putting here again this white dwarf luminosity function. So once again, this is just how many white dwarfs there are per different luminosity bin. And evolution of white dwarfs here goes from left to right, so from hot and luminous to cool and dim. So one thing I've not said earlier is that this cutoff that we see here is not an observational artifact. It's directly related to the finite age of the disk of our galaxy. So white dwarfs just did not yet have the time to cool down to lower luminosities than this cutoff. Okay, so let's look at our crystallization pilot. So first, if we use white dwarf models that don't include any core crystallization, this is what we find. So we are completely underestimating the number of objects that is here, which is to be expected because we don't have those new energy sources that slow down the cooling of the white dwarf. Now, if we include our new phase diagram in there, that's what we obtain. So the fit overall is pretty good. But in particular, an improvement that we have compared to the results that I've shown earlier is that the location of this bump is now aligned with the observed location of crystallization. So this rise here in the luminosity function closely matches the observations. But we still have this problem that we are underestimating the number of objects at the peak of the crystallization pilot. So now that we've done all this work on carbon-oxygen plasmas, we are confident that we understand the physics of what's happening, and we think that what's to blame for this gap here is the role played by a third species that is present in white dwarf cores, which is neon 22. So neon 22 is really just a trace species in white dwarf cores. So we're talking about only 1 or 2% maximum of the white dwarf's mass. So it basically comes just from the leftovers of the hydrogen burning phase of the star. So during the CNO hydrogen burning cycle, this step here is the slowest one, which means that when the star runs out of hydrogen to burn, there is a pileup of nitrogen-14 that is still sitting there in the star. And later on during the evolution, this nitrogen-14 can capture helium ions to form neon 22. So that's how we end up with this 1 or 2% of neon 22. So the key with neon 22 is that it's a neutron-rich isotope in the sense that it has its number of neutrons is it has 2 more neutrons than protons basically, and because of that it means that if you phase separate a given quantity of neon 22, you will be releasing 25 times more gravitational energy than if you release the same quantity of oxygen 16, for which has no excess neutrons. So it's because of those 2 excess neutrons that even though neon 22 makes a small fraction of the white dwarf's mass, it can have a disproportionate effect on the white dwarf cooling. So to know if neon 22 phase separates in white dwarf cores, we need to know the shape of the carbon-oxygen-neon phase diagram, so the ternary 3-component phase diagram. So this is something on which we're working right now, but we already have preliminary calculations that indicate that yes, there is a phase separation of neon 22, and that this phase separation actually operates quite differently of what we had with oxygen 16. So what seems to be happening is that at first the white dwarf crystallizes without neon phase separation, so you have as much neon 22 in the solid as in the liquid, but eventually when about 2/3 of the white dwarf is already crystallized, then you start to have phase separation of neon 22. But it's very different because now the solids that are formed are neon poor compared to the liquid. So remember with oxygen we had oxygen-rich solids. But now we have neon poor solids, and this neon pore solid will be lighter than the surrounding liquid, which means that it will float upwards in the white dwarf. And by floating like this, it will displace liquid close to the crystallization front, and this liquid will contain more neon than what we add in the solid, which means that gradually we are increasing the concentration of neon close to the crystallization front, and eventually it's enriched enough that we reach the azeotrope point and everything freezes at this azeotropic concentration. So what we've done here is that we've effectively taken all the neon that was in the liquid part of the core, and we have pushed it down into a thin layer at 2/3 of the white dwarf structure, and this, of course, releases gravitational energy, and this accounts from our preliminary calculations for another cooling delay of about 1 billion years. And it turns out that it's almost exactly what we need to fill the gap between the observations and models for the white dwarf luminosity function. So I'm very confident that this is the missing ingredient in current cooling models, but we have to complete those calculations to be able to know this number as accurately as possible. So just a quick summary before moving to the questions. So white dwarfs are very useful for astronomers because they allow us to measure the ages of stellar populations and better understand the history of our galaxy. But this kind of application depends on accurate white dwarf cooling models, and now we have new observations that tell us that they are not as good as we would like to think they are. So we have to work on the physics of those models. So we have developed a new simulation capability to accurately and efficiently model phase transitions in white dwarfs, and it seems to well, it's heading in the right direction to improve the match between the observations and the models. Also, this new simulation capability is now ready to be applied to other systems, so other things than plasmas. I mean, we just have to change the potential that we're using. So thank you very much for your attention. And well, if you have any questions, I'd be very happy to hear them and try to answer them. Thank you.
Thank you very much for the very talk. I invite everybody to give Simon a nice applause. And we already have some questions in the chat, and I'll start reading them. Feel free to add to those. So first, there's a question from Schweizer. Is it known for sure that white dwarf solidifies starting from the core? If there is convection and the adiabat is steeper, then the solidification could start from the middle.
From the middle? I mean, the middle is the core. No? Well, the thing is, okay, so the core is basically isothermal, so it's the same temperature across all the core because it's very conductive. But you have a steep density gradient because that's how the white dwarf can, well, avoid to collapse. You have to have this density gradient to maintain hydrostatic equilibrium. So in the center, the density is much higher than anywhere else in the core. So that's where you reach the right coupling parameter first to undergo your crystallization. So when the center reaches those conditions, the rest of the core is far from reaching the right density for crystallization. And later on, the rest of the core will not become denser, but it will become cooler. So that's how you reach the right coupling constant to start to solidify later on.
Okay. There's a question from Philip Mike. I think the Gibbs-Duhem equation you're using is an approximation that is applicable only for nearly pure mixtures, where the excess component is nearly ideal. And as a result, you can approximate the enthalpies in the mixture with the enthalpies of pure components. Is it still applicable over a wider composition range? like in the middle of the phase diagram, we have a 50-50 oxygen-carbon mixture?
Well, as far as I know, it's not an approximation. I mean, I've gone through the derivation once, but I don't really remember the details. Yeah, I don't know what else to say. I think it's accurate, and I think our calculations show that because we have this good match with the molecular dynamic approach. Yeah, so I'm not worried about that.
Phil, would you like to unmute and clarify?
Well, I think the equation, I mean, I believe it is only applicable for for ideal mixtures, or if it's non-ideal, you can use it as an approximation when you're, very close to being pure, like 99% oxygen or 99% carbon. I don't think it is applicable outside, because you're using things like the enthalpy of like a pure component. And, when you have a mixture, your enthalpies can be really different.
No, but we're not using the enthalpies of pure components. I'm not sure why. So what goes in the equation is the enthalpy of the liquid and the solid at a given fugassity fraction, but it's not a pure at all. I mean, the Monte Carlo calculation give us the enthalpies. For a given concentration, from first principles, basically. So.
Okay. All right. Then I misunderstood. I thought you were using the pure component.
No. So the enthalpies there are there for the liquid and solid, but it's at a given concentration, at a concentration that is given by our fugassity fraction.
Okay.
There's a question from Nathaniel Roth. In addition to affecting the cooling rate, do the depths of the details of the crystallization affect the mass radius relation that is used to infer masses?
So there is a small change of volume during crystallization, but it's very tiny and it does not significantly affect the mass radius relation. So the thing is that what dominates the white dwarf structure is the electrons, the degenerate electrons. That's mostly them that provide the pressure to maintain hydrostatic equilibrium. And that's why there is only a very small change in the radius of the white dwarf when it crystallizes. The ions are not so important for the whole structures.
I apologize. I seem to have some questions by accident. There's a question from Michael Demkowitz. What is known about the structure of the crystallized core? Are the lattice units all known? Does it start out as a polycrystal and then coarsen into a monocrystal over time? Does the crystal contain defects, vacancies, dislocations, etc.?
That's an excellent question, and we don't know. We don't know. The only thing we know is that the BCC structure is the most stable for this for a carbon-oxygen mixture, but we know nothing about the dynamic of how this happens. So, that's something we should probably look into. But then there's a problem of does it change something to the models, and can we test any of that? I guess that's why people have not looked into that, but it's a good question.
Just to quickly comment on that, I suspect, I mean, obviously I don't know, but I suspect that if you have an accumulation of defects, or if you start out with a polycrystal that then coarsens, you could have a delayed release of some heat. Because as the crystal shakes down to a single crystal, over some longer period of time, it could be releasing more energy. Yeah.
Usually people brush those, because all this takes, it occurs over hundreds of millions of years. So we tend to just say, well, there's enough time for all this dynamic to average out, and we don't have to care about it. But yeah, who knows?
Okay, and there's another question from Philip Knight. The temperature composition oxygen carbon phase diagram show is for a particular fixed pressure. If you change the pressure, the phase boundaries will change. Can you draw conclusions about core crystallization from a single phase diagram? since you showed that the crystallization front propagates from the core to the outside. And I suppose that the pressure changes very dramatically in different regions of the white dwarf.
Yeah, that's something that we've explored because, indeed, in general, the phase diagram won't have the same shape at different pressure, but we've computed this different version of this phase diagram for all the pressure range relevant for white dwarfs, and it's always the same shape. And the reason for this is that it's really the electrons that dominate the pressure, so it does not change anything for your ions to change the pressure. If we were going to lower densities where the ions start to account for more of the total pressure of the system, then yes, you would start to see important deviations, but it turns out it's not important for the range of pressures relevant for white dwarfs.
Okay, and there's a question from Dr. Bunsen, aka Joe Holder. Is there any observational white dwarf ring info?
Sorry, I missed the question.
Is there any observational white dwarf ring info?
Ringing?
Seismology type stuff.
Oh, yeah. We have white dwarf seismology is a big field of white dwarf study, and you can, it changes if the quartz crystallizes. It changes the signature of your the modes that are excited. So yeah, this is a rich field of study of white dwarfs.
And a question from Bruce Remington: can aspects of the models of white dwarf core solidification be tested with scaled experiments?
That's a good question.
Well, I think the physics is not. The physics is quite well understood. Actually, it's just a matter of doing the computation because the plasma is completely ionized and all that, so it's. I wouldn't be able to justify an experiment in this regime where really we just have bare ions and degenerate electrons. The physics is quite easy overall, so I don't. Yeah, but can it be done? I don't know. I don't know if there's a scaled experiment that could be done for that. But, yeah, good question.
I imagine there's like dusty plasma experiments might be relevant.
Yeah. Well, then I guess the real problem is how you relate those to white dwarfs. But,
so Felipe asks, did the two-phase simulations include all the electrons, or did they have some frozen core electrons? Otherwise, the plasma would not be completely ionized.
Well, no, so the electrons are just there using an electron genome that we add on top of the ions dynamo. Yeah, so it's it's completely ionized. It's just we take the total charge of our system, and that's how much electrons we have. We get the electron density, and from that you have all your usual equations to know the pressure and energy and all that of your electron genome. So no.
So I had a question that would dust raining down on the white dwarf mess up the chronology, and you're able to take into account in a simple way?
Accretion by the white dwarf?
Yeah.
Yeah. Well, it can change. No, it won't change much about the cooling history of the white dwarf. So the worst that can happen is if you accrete a large quantity of hydrogen. The hydrogen is quite opaque, so it slows down the cooling, the white dwarf. But usually the kind of quantity that you accrete are too small to have any significant effect on the white dwarf cooling.
Or what if there are metals that are falling and then sink down to the core and produce an extra heating mechanism.
Oh yeah, well, yeah. So if you accrete things heavier than helium, so yeah, they will sink down to the core within a few million years. But the quantities we're talking about are very small compared to the overall size of the white dwarf. But one thing that's very interesting, though, is that we now know many examples of white dwarfs that accrete not just interstellar dust or whatever, but they accrete rocky debris from their own planetary system. And in those cases, those white dwarfs are very interesting because by looking at their spectrum, you can deduce, you can trace back what was the composition of their comets or planets that were around them previously. So that's something we can do. But for white dwarf cooling, it's not, not a problem.
Neat. Okay. I think that's it for your questions. So let's thank Simon Blouin again. Please unmute. There.
Thank you.
Thank you.
And thank you again for the very nice talk. And I hope your project almost goes well.
Yeah. Thank you.